This video introduces the idea of associativity in caches. To motivate this idea, let us recall this example we had seen with the direct mapped cache. We had a cache of 8 blocks, each block being 2 words, and a particular memory access sequence given this sequence of memory word addresses. We had found that word address number 17 and word address number 0 mapped onto the same cache block, that is cache block number 0. So when 17 is accessed, it evicts the earlier fetched word addresses 0 and 1, and this results in a cache miss when word address number 0 is accessed subsequently. Note that 17 evicts the earlier present word addresses 0 and 1 from block number 0, even though there is plenty of empty space in the cache at the point when 17 is accessed. So the cache miss which happens when 0 is accessed next is known as a conflict miss, because this happens because word addresses 17 and 0 happen to map to the same cache block. They have a conflict in the cache block, that is, only one of them can be present in the cache at any given point of time. Now suppose the program continued, and suppose we had a loop where word addresses 17 and 0 were accessed repeatedly one after another. What do you think will be the hit ratio in that case? Well, what will happen is that word addresses 17 and 0 will keep kicking out each other from the cache, and this will result in all of the memory accesses being cache misses, resulting in a hit ratio of 0. Well, that's not too good. This can happen in real programs. We have a problem with the cache design then. What do you think is the main culprit here, which is causing this performance problem? We can narrow down the main culprit to the many-to-one mapping of the direct map scheme. So even though there is plenty of empty room in the cache, the direct map scheme is forcing word addresses 17 and 0 to map to the same cache block, which is resulting in them evicting each other when accessed in a loop. Having identified the problem and the main culprit, let's see now how we can fix this. Since the main culprit is the many-to-one mapping, the idea of associativity is essentially fixing that. Now we are going to say that a block of main memory can reside in any cache block. That is, now the main memory block number to the cache block number is a many-to-many mapping. This scheme goes by the name of fully associative cache because a block of main memory can be in any cache block. So if we have such a scheme, this can reduce the kind of conflict misses which happened earlier in the direct map cache. Well, nothing ever comes for free. There is a price to pay for having associativity in a cache. In the direct map cache, the cache controller, given the memory address, could easily find out the block number where that particular data corresponding to that memory address potentially resided, and check the valid bits and tag bits for that particular block to determine whether there is a cache hit. However, in this fully associative scheme, given a memory address, the data corresponding to that memory address can be anywhere in the cache. So now we have a problem of searching through each of the blocks in the cache to check if that particular memory address we are interested in is currently residing in that particular cache block. So instead of just checking one tag, we now have to check in parallel several tags. Each of the tags corresponding to each of the blocks in the cache have to be checked against the tag field in the given memory address. So in the earlier scheme, memory address was looking like this. We had a field for word number in block and a field for block number in cache, and then the remaining MSB bits was the tag. Now there is going to be nothing in the memory address which tells the block number in cache, because that particular memory address could have been mapped to any block in the cache. So we still retain the word number in block field, and the rest of the bits in the memory address correspond to the tag. So not only has the number of comparisons increased, the number of bits to be compared, that is the number of bits for the tag, has also increased now. So associativity reduces conflict misses. The kind of conflict misses we saw in the direct map cache will not arise in a fully associative cache. On the other hand, there is a price to pay in terms of comparator cost. There is extra hardware which must be added to the cache controller. Not only that, we are going to pay a price in terms of performance as well. The hit time is going to increase because now we need a lot of parallel comparisons, each of which involves many more number of bits than earlier. Increasing the hit time is especially bad because in a cache we expect cache hit to be the common case. So if we are slowing down the common case, that is a bad thing to do. So in trying to fix one problem, we seem to have introduced a few others. Let's see now what we can do. So here is the next neat idea. We are going to use what is known as set associativity. So in direct map, we had one block of main memory mapping to exactly one cache block. That is, it can be found in exactly one cache block. In the case of fully associative, a block of main memory can reside in any cache block. With set associativity, we are going to take a middle path. We are going to say that a block of main memory can now be in any of a set of cache blocks. That looks like an interesting approach. Let's see how we can make it work. So in a set associative cache, we are going to divide up the cache into multiple sets. And a set itself will consist of several blocks, and like earlier, we will have each block which can have many words. So how is the cache controller going to handle memory access given a memory address? In direct map, we had these fields in the memory address: word number in block, block number in cache, and the remaining MSB bits as tag. In fully associative, we only had word number in block and the remaining bits as tag. In set associative, what we have to do is, given memory address, we need to find the set number in which that particular memory address can potentially reside. So corresponding to this, the memory address is going to have a field for set number in cache. So in this example, can you tell how many bits we need for determining the set number in cache? Well, this is directly given in the diagram here. We need 2 bits because there are 4 sets in this cache. Now can you tell how many parallel comparators we are going to need in this set associative cache? Remember, in a set associative cache, a particular block of memory can be in any of a set of cache blocks. The memory address will directly give us which set that particular memory address could potentially be in. Within the set, we have to do a parallel comparison of the tags. So the number of parallel comparators that is going to be required is nothing but the number of blocks in the set, which in this example is 2. So we have seen 3 kinds of cache design: direct map, fully associative, and set associative. Well, it turns out they are all different points of design in the same design space continuum. In the case of direct map cache, it is nothing but a set associative cache where the set size is nothing but one block. So we could potentially call it a one-way set associative cache. In the case of fully associative, we can consider a fully associative cache as nothing but a set associative cache with exactly one set. And the size of this set is going to be k, where k is nothing but the number of blocks in the cache. So we can also call this a k-way set associative cache. And the set associative cache we looked at is something with a set size in between 1 and k, and this would be called an S-way set associative cache, where the set size in terms of number of blocks is S. Well, isn't that a neat way of putting together these apparently different looking designs in the same perspective? I told you memory system has several appealing things in its design, and this is one of them. Just to make sure you understand set associativity very well, let's go through a numeric example. Continuing along similar numbers like in an earlier example, let us take a main memory with size 32 megabytes, cache size 512 kilobytes, and block size of 16 words. In this case, we are going to have an 8-way set associative cache, that is, set size is 8 blocks. For this case, can you show the various main memory address fields as interpreted by the cache controller? Well, the last few bits are going to be the same irrespective of whether we have direct map or fully associative or set associative. The last 2 bits correspond to byte number in word, which will be 00 for a word aligned byte address. The next few bits are going to be word number in block, which in this case is going to be 4, corresponding to block size being 16 words. The next set of bits are going to represent the set number in cache. Here is where we are going to see something different from the earlier example. Earlier we had counted the number of blocks in the cache in the case of direct map cache for determining the number of bits to represent block number in cache. Likewise, here we have to determine the number of sets in the cache to determine how many bits are required in the memory address field to represent the set number in cache. So let us do that. Cache size is 512 kilobytes divided by the set size. Set size is going to be 8 blocks, where block size is 16 words and word size is 4 bytes. So if you do the arithmetic, you will find this to be 2 power 10. So this is the number of sets in the cache. So we need 10 bits to represent set number in cache. And then the remaining number of bits, which is 9 in this case, is going to represent the tag field of the memory address. Now can you tell in this set associative cache scheme how many parallel comparators are we going to require? The number of comparators required is nothing but the set size in terms of number of blocks. So we need 8 comparators in this case. And can you tell each of the comparator in the parallel comparators, how many bits does it need to compare? Well, it needs to compare 9 bits, which is the same as the tag size. One important design component in the design of a set associative cache is what is known as the replacement policy. This refers to what is the scheme we are going to use to determine which cache block to evict when the set is full and another cache block from main memory is going to come in to the same set. Now, of the 3 possible cache designs, direct map, fully associative and set associative, for which kind of design does this policy not matter or is irrelevant? Well, for the direct map scheme, there is no point in talking about any replacement policy because we really don't have any choice. The set size is 1, and if the set is full, that is, if that particular cache block is occupied and another main memory block wants to occupy the same cache block, there is no choice. That particular cache block which is currently resident has to be evicted and replaced with the new incoming memory block. Can you think of some possible algorithms for determining which block to evict within a set? Here are some possibilities. First, we can just randomly evict any block from within a set. Or we could say that whichever block came in first into that set is going to be kicked out first. This is a first in first out or FIFO policy. The next two possibilities are based on the usage of the blocks. So for example, in this particular example, let us say within set 00, block 0 is less frequently used than block number 1. If this has been the case so far, we expect that the program will continue this behavior. So we may choose to evict block number 0 because it is less frequently used compared to block number 1, or rather what is currently resident in block number 1. Another scheme which tracks the usage of the blocks to determine which one to evict is the LRU or least recently used policy, where whichever block was least recently used from among the blocks in a set is going to be chosen for eviction. That data is going to be chosen for eviction. In practice, it has been found that LRU is quite effective. However, implementing the LRU policy exactly is going to be difficult in hardware, because implementing it exactly will require you to maintain timestamps, and that is all too much overhead, especially in hardware. So what is actually implemented goes by the name of clock algorithm, which is an approximation of LRU, and it is found in practice that the clock algorithm works quite well. What exactly do we mean by working quite well? That is, it leads to lesser miss ratio in the long run. Although I have mentioned the name clock algorithm here, an actual discussion of the algorithm itself is outside the scope of this course. Also outside the scope is a more comprehensive treatment of the design trade-offs of these various possible algorithms for the replacement policy. The replacement algorithms are discussed in detail in a typical operating systems course. This is because the same algorithms which are relevant to cache block replacement are also relevant to the context of virtual memory, where main memory acts as a cache for virtual memory, and in that context the replacement algorithms are implemented by the operating system. In our context, that is the cache memory which resides between the processor and the main memory, the replacement algorithm is implemented by the cache controller, and it suffices for us to know that LRU works well in practice, and what is implemented is an approximation by the name of clock algorithm, which also works quite well. To summarize, we have learned associativity as an idea to reduce cache conflict misses. We saw that the fully associative scheme, while being effective in reducing cache conflict misses, it is too expensive both in terms of hardware cost as well as in terms of performance due to increase in the hit time. We found that set associativity is a nice middle ground to get the benefits of full associativity in terms of reduced conflict misses, and also benefit of direct map in terms of low hit time. And we saw that we need to have something called the block replacement algorithm, and in practice the least recently used or LRU algorithm works well. Next, we are going to look at various facets of cache performance and how it can be improved.